Hey guys, so I'm going to go ahead and show you now propositional logic subproofs, and after that we'll look at some actual examples where we'll look at techniques of doing proofs. So remember, a proof is where we take an argument that has a certain number, so any argument, right, is just a list of premises, a list of reasons that we think entail some conclusion. Right, so the idea is if these are true, then the conclusion also has to be true, right? So that's what makes an argument. That's what it means for an argument to be valid, that if we accept that the premises are true, that they entail the conclusion. Then verifying whether or not the premises are true, right? Then maybe you make another argument where the premise is a conclusion or something like that. Or maybe you do a scientific study or something like that. That's not what we're going to focus on here. That's going to be about philosophy and science and things like that. But the idea is we're saying if you assume that these are true, if you assume that our premises are correct, does that force the conclusion to be correct? In this hypothetical world where you have both of these things being true, does this automatically come for free? Right. So that's what we're interested in doing with proofs. Right. And so far, just with inference rules, all that we can do is just things like, okay, because you believe these two things, I can show you believe a new thing. So let me actually just say new thing. And the idea is I would justify it by a rule in the lines. So the idea here is I'm saying, okay, we're starting off, me and the guy I'm arguing with or whatever, we're starting off both agreeing on 1 and 2. We just agree on 1 and 2. And the idea is, so far with these rules is, I can take those two lines, and so long as they fit into the structure of the rule, I can get the new thing. And the rule is going to tell me that new thing, right? So if my premises are, premise 1 is P or Q, and premise 2 is not Q, the DS rule, what am I doing? The DS rule says if you ever have, and I'm not even going to write these things, I'm going to try to refrain from writing these things with letters and writing them with the scopes, because I think that's more visually helpful to a lot of us. So DS, right, is going to tell us just that if you have a premise that looks like this, and you have another premise that looks like this, you can get that guy, right? So what does that mean? It just means we're just going to scan our premises. First, you scan it for this guy. So, oh, look at that. One of my premises fits that guy. And then next you scan, okay, well, do I have the second part I need, right? So for the second part, I need all of that. Oh, look at that. So here, the red side or the right side is just Q. And so I just need to match that Q up with the red right there. And I need to make sure not only do I have that Q, but I also have a tilde on the side. And that's exactly what this is right here. And so then the idea is, oh, that means that means it's going to give me the green at the end of the day. So that means at the end of the day, I can actually put in P. And how did I know I put in P? I'm just taking whatever it was that was on the left side of that OR, right? So all these inference rules that we learned, these are all just going to be, just scan the lines that you already have. Are there any perfect matches? That's the only thing you can ever do with an inference rule, whether that's an implication rule or an equivalence rule. You just have to scan, do I have a perfect match? If you have a near miss, then you can't do anything still unless you can use a different rule to get you close enough to using that rule, right? And so this is the sort of thing like if Q was actually a negative Q and we didn't have that there, then in fact this wouldn't be a match for DS, and we would have to do a little bit more. We'd have to do a double negation on Q. But that's the sort of thing we'll talk about as we get to actual examples near the end. But what I'm just trying to remind you of is at this point, without subproofs, all that we can do is just scan the premises that we actually have and see, is there anything that perfectly matches any of our rules? And when you're thinking of perfectly matching our rules, you want to be thinking of this in that sort of lens of just left versus right. And that's just about identifying what's the main operator in your premises. Right? Okay. So that's what we have up to this point. But what happens if you're doing a proof so, well, there's a variety of things. There's a variety of reasons you might want to do a subproof. So let me just go ahead and clear this away now. So far, that's how every proof has gone. So after you have those first two lines, every new line you give would need to be justified by some rule and the lines that you're applying that rule to. Right? So that should just be we should be very comfortable with that before we move on. That just generally speaking, proofs should be working by just making one step. All right. Now, it's important that we understand that everything has to be justified here because that's different than what we're doing with subproofs. We're making a change when we get into subproofs. So let's say I had a proof that something like this. 1, 2, so either P is true or Q is true. And then let's say if Q is true, then R is true. And let's say I want to convince you, I think those are two good reasons to believe that if P is not true, R has to be true. Right? So what I'm claiming here, right, what an argument is saying is these, if you believe anything of this form, then you should believe this too. Right? And again, it doesn't matter what this is about. If you believe that you're either getting a dog or you're getting a cat, and if you get a cat, then your little brother will complain. Then you should believe if you don't get a dog, then your little brother is going to complain. Right? So that's all this argument is trying to say. It's not saying that these things are actually true. It's just saying if we start off believing that these things are actually true, you better believe that this is actually true too. And so what we can do here is we can try to scan through our various rules to see, okay, how can I get from here down to here? Now, this problem we would be able to figure out how to make it we would be able to use our simple rules to get to this conclusion. And so, well, let's just go ahead and do that just for the practice of it. So for instance, if you right, well, we could use implication rules and equivalence rules to make this proof. But honestly, it's a little bit more subtle, and especially at this stage, you'd be doing things that, I mean, right, as you get more experienced, it might seem more obvious to you, but at this point, it wouldn't be. So the first thing I notice is I want this conditional, right, that's going from not P to R. Well, here I have what looks like basically an HS match, right? So HS is the one that says if P then Q, Q then R, just means you can cross out the Q and you know that P leads to R. So really, instead of this or, I want to think about it as just a conditional, right? And so for that I have the MI rule. But it's not a perfect match for MI. I would have to do a double negation to the P first, because the MI, in order for that to work, you need a tilde on the outside of that or. So if you're confused by this explanation, I mean, that's might not be surprising because I haven't talked about the techniques for doing these things. And ultimately, this proof is going to be much easier once we have the subproofs. But the idea is if you wanted to prove this just based on our simple rules, we would have done a dn to 1. And then we would have done an mi to 3. So our new line, now I'm changing that to be tilde arrow q. And then 5 would be an hs, right, between 2 and 4. That'd be, so I would just take the left side of this conditional, and because it leaves off with q, and this conditional picks up with q and ends with r, I just get to say, okay, then that means p, not p, is actually going to lead to r at the end of the day. And just like that, I finished the proof, because my last line is exactly the same as my conclusion. Now, that you might be thinking like, okay, I'm not sure how you saw that. And I mean, I didn't give too much explanation on how I did. And the reason is because this proof is going to be much easier for us to do with our subproofs. So the idea is, so the first subproof we're going to look at, I'm going to write the same thing down over here. I'm going to do a different color. P or Q, Q arrow R. The idea behind a subproof is we're going to basically just give ourselves, I mean, not just basically, we really just are going to give ourselves another assumption. And this is going to be something that we're completely unjustified in writing down right now, right? So normally I would put a rule, I would put exactly how I know that line is justified. It came from these 2 lines, and I'm just applying this rule to them, right? And every rule is just itself just a very innocent little valid argument that we should all be able to understand. So it should be very obvious how I get each and every new line. But with the assumption, I'm not justifying this new line. I'm just writing it down. So the idea here is I'm just starting a new story. And I'm not guaranteed to believe what I put here, so that's why I'm putting this line to kind of remind ourselves like, okay, like I'm starting a hypothetical here. So in this case, what I want to do is I want to prove to you this, right? This is my goal at the end of the day. I want to prove to you that if not P is true, then R is true. So the idea is I want to say, well, let me assume just for a second, let's just both assume that not only are our premises true, we're all assuming that always, but we're also going to just assume P. And the idea is I'm going to try to show you that if we can assume P, then you should believe R at the end of the day, right? And the point of that isn't to convince you to actually believe that R is true, just outright. That's not what's going on. The point is to prove to you that you should believe R is true if you ever believe P is true, right? And that's exactly what my conclusion is. So a subproof is always going to start off with a new assumption, and it's going to be saying, based on this assumption, I'm going to show you some end, right? Based on whatever I start with, I'm going to show you how things are going to turn out. And then what we do is we always end this subproof. So a lot of times you don't just see a bar next to these lines, you're going to see it like kind of bracketed off. Like this is a little story. It starts on that line, these still get line numbers. But the idea is I can't end the proof while I'm inside this story. I need to stop the story and say, okay, based on this, based on what we've done here, I can turn around and say that not P really does lead to R. And the idea is now this part is not an assumption, right? So down here, these guys, this has actually been justified, and it's been justified by a conditional proof. So conditional proof. And why do we call it a conditional proof? It's because you're proving a conditional, right? This conclusion here, the form of the sentence you just proved is always going to be a conditional for a conditional proof. So the idea is Right, so this wouldn't be line 4 that we're able to get to that. It would be, so we would first have to do a ds to get to not q, and then we would do a exponent. So I'll actually walk through those steps in just a moment. But the idea is we would have had to tell a story, and it takes 3, 4, and then all the way up to line 5 for us to finish that story. So I'm not just citing this line and this line, I'm citing this whole chain of reasoning. So that's why it's going to be 3 through 5 for the CP. And so then the idea is, all right, without this in the middle, without even knowing where I'm going to end up, so until I've actually finished this subproof, I'm not sure what those lines are going to be. But the idea here is, now all I need to do is show how, based on the assumption of not P, I can get you to R, right? That's all I need to do now. So now I get to use not P, and I still get to use my premises, right? We're just always assuming that these are true. And now all I need to show is that R is true. And if I can show you, based on this assumption, that R is true, that's what it means to show that the assumption really does lead to R, right? So now the only thing we need to do is actually make the subproof work. And then this just comes for free, right? And so to do that, I already showed a little bit. All we're going to have to do, so we have not P. So with 1 and 3, right, that's just a perfect match for DS, right? And so DS says if you ever believe P or Q is true, but you know that one of those isn't true, then the other one has to be true. And then right away, we can get to R because we have a perfect modus ponens match, right? Now we have Q, and we have if Q, then R. And so then we actually get R. So that's just modus ponens. And then what lines? 2 and 4. So just to be clear, for those of you who are still getting used to it, why didn't I cite 1 for line 5 here? Well, because 1 has absolutely nothing to do with modus ponens. Think about what modus ponens actually looks like. Modus ponens is saying that, right, so why is it invisible? Modus ponens is saying that if you have one side, boom, 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 right? So that's modus ponens, right? So modus ponens is only ever going to be looking at 2 lines. So one of the common mistakes people do is they try to cite everything that they used in order to get down there. And that's just, again, completely missing the point of doing a proof. The whole point of doing a proof is that you're slowing it down so just every single little step you do is a completely innocent step. And each little innocent step, you only have to look at just 2 things or just 1 thing, depending on the rule. Anytime you ever do modus ponens, you should be able to pick out, okay, that guy's my conditional, and that's the left side of my conditional, or vice versa, right? Just one of my lines is a conditional, and one of my lines is the left side of that conditional, right? So here, let's just erase those. So here, all we did was we just noticed, okay, that matches there. That matches there. All right. So that's all that modus ponens is. And so then you just look for, okay, that's there. That's line 2, right? Line 2 is the conditional, and then the other line that we needed was line 4, and that's what gives us line 5, right? So modus ponens is always citing 2 parts. Okay, getting a little bit away from the topic. But just to, you should always be comfortable with what's going on in modus ponens. All right, so this way of doing it, once you're comfortable with conditional proof, is actually going to be just a much more intuitive way of doing proofs. So the idea is, let's go ahead and look at just a more complicated example. The idea is, anytime you ever have a conclusion whose main operator is a conditional, it is going to be so much easier to do it as a conditional proof, right? So if this is our sentence, right, that if A and B are both true, then C is false. Well, let's look at right. Let's look at how this could go. So A implies A implies D might be one premise. B implies F might be another premise. 3 might be I don't think I like this example terribly much. Right, so we'll do another example like this and just let me make this just more intuitive to what I was thinking about. So the idea is anytime we have a conditional proof like A and B, arrow, C and D, instead of just thinking of, okay, so let's say A actually leads to B and, oops, no, not that, but A leads to C and B leads to D. Right, so let's try to do this proof. So the idea is we think these two things are good enough reason to believe this thing, right? So we think that if it's true that A leads to C and it's true that B leads to D, then it should be true that A and B together lead to C and D together, right? That should be an obviously valid argument. If A and B are both true and independently they lead to C and D respectively, then if both of them are true, then we know C and D are both true, right? But it's not exactly clear what rules we can do here, right? So if we tried to do modus ponens, well, can we? No, right? So I'm going to leave modus ponens up in the corner over here. And you know what? No, I'm not. Just because that's probably going to be erased in a minute. Okay. So the idea between modus ponens is, okay, we have this left side and we have this right side, and the only way I could do it is if on some other line that I already have, I have the right side, and then I could give myself, or I have the left side, and then I could give myself the right side, but we can't do that right now, right? So there's really not much we can do here. But what we want to do is anytime, you always want to check, is my conclusion a conditional? Because if your conclusion is a conditional, really what you're trying to prove is if A and B is true, then C and D is true. So what we're going to do is we're going to say, well, okay, just assume A and B, and I'm going to try to convince you of C and D. And again, the idea is if we can make this work, if we can show that A and B really do lead to C and D, then that's all that it means to show that A and B really do imply C and D, right? So all we need to do is make this story work, and then that's what it means to really show our conclusion. And that's true every single time your conclusion is a conditional. So that's the first rule, or the first technique I would suggest for doing proofs is check, is my conclusion a conditional? Because if it is, just assume the left-hand side of that conditional. And then at the bottom of it, you just want to somehow do old school logic to get to the bottom. And then if you can do that, the last line is justified just by CP, whatever that line, whatever it starts on and whatever it goes to, 3 through number. Okay, and now all that's left for us to do is fill in the gap right here. That'll give us what number this actually is. We can fill in, and we're absolutely done. So whenever you're doing this, it's important, don't just start off a CP and just assume something and have no idea where you're going. It's absolutely vital that you put all this information down right away. Okay, so again, this may be a little bit of overkill. So if you're comfortable with this, feel free to skip ahead just a little bit. But the idea is, as soon as I see that my conclusion is a conditional, I'm going to have the following reaction, right? So the first thing I'm going to do is I notice, okay, my conclusion is a conditional, so I'm going to take my left side, and I'm going to look at my right side, right? So the name of the game with understanding these rules generally is always, right, it's just going to be about, okay, what's my main operator? And understanding your main operator is really just about understanding what's on the left and what's on the right and treating them as full units. And now all I'm going to do is I'm just going to take whatever was on the left side, whatever it was, and I'm just going to put it at the top of the subproof. This is invisible when it's. And put whatever's on the right side at the bottom of the subproof. And then at the idea is after the subproof, I get exactly what my conclusion is. So this is the structure for conditional proof. So first you check, is my conclusion a conditional? And as soon as you see that it is, put it in that structure. And that there should be no confusion here. You should be excited when you see that your conclusion is a conditional, because it should be super easy to put it in this structure, right? What's in the green box? A and B. What's in the red box? C and D. Same thing. A and B is in the green box. C and D is in the red box. It literally exactly the same every time. Don't confuse it. Just identify your main operator. If it's a conditional, you do this. Okay. Now another question you might have is, why didn't I do a subproof like this? Why didn't I do A leads to C? Well, if you're thinking that that was a good subproof to do, you're not understanding what we're doing with proofs, right? What would this have done? What would a subproof starting with A and leading to C have done? It would have proven that A leads to C. Why would you have wanted to prove that A leads to C? It's a premise right here, right? Remember, premises are things we already know are true. A conditional proof is proving that something is true. It's proving that a conditional is true. So if your premise is a conditional, you don't need to do a conditional proof on it. You can just act like that was already done. You already know that A leads to C. So one of the mistakes I see all the time is somebody sees that the premise is a conditional and they break it down as a conditional proof, and that just automatically, I know that you have absolutely no idea what's going on in a proof. Like, that's just, there's just no getting around that. If you're trying to do a conditional proof on a premise, then that must mean that you don't understand that you're accepting that your premise is true, or you don't understand that a conditional proof is proving that thing, right? But because why would you ever want to prove something that you already started off believing is true? We're trying to prove something new, not something old. Okay, so that's just one of the weirdest issues I see people making, is trying to do a CP on a premise. That just doesn't make any sense. Stop it. Okay. So now all that we need to do is just make this story work. We just need to make it so that A and B really does lead to C and D. And now basically we just get to think about this as just a regular logic proof, but now we have 3 premises and just a single, much more simple conclusion, right? So now A and B, right? Whenever I have a conjunction, it's always going to be very useful to break that apart. So that'll be, oops, I don't know why I jumped the gun and put a 4 down here. I don't know what line we're going to end on. So 4 and 5. So this first one, we always write assume, because that's the start of the subproof. We assume that that's true. But everything after that first line of a subproof needs to be proven, right? Unless you're starting off a whole new subproof, you need to prove this. So the idea is this is just going to be 3 simp. This is also 3 simp. And then 6, we can do a modus ponens with 1 and 4. And so we can think backwards. like even if you didn't know exactly what I was trying to do right here, you can just see, oh, he's doing a modus ponens and he's doing it to 1 and 4. All right, 1 is a conditional, 4 is the left-hand side of that conditional. Modus ponens tells me that if I have the left-hand side of some conditional, I get the right-hand side, right? So that's all. So just by the citation on the right, you should be able to see exactly what is going on in the proof. Okay, and so we're going to need a little bit more room here. So I'll go ahead and erase this. Although that's still, we need to keep in mind that that's what we're trying to get to. But 7, we're going to need to do a different modus ponens. This one's with 2 and 5, right? And that's also modus ponens. But this one's going to give us D. So that's that conditional with that left-hand side. And then on 8, finally, now we can conjoin it. Now we can get to that last thing we wanted. So that's, we point out to him, hey, you believed 6 and 7, and I'm just going to conjoin those things. And so, right, and so now, just recap what we've done. We haven't just proven simply that C and D is true, just bar not, like just without any qualification. What we've done is we've said, okay, if you just give me this assumption that A and B are true, then you certainly have to agree with that. Then you certainly have to accept C and D. And right, and so the idea here, and this is the idea behind just a CP generally, is that if you just grant me some assumption, I'll show you that something holds. And that's all that it means to show the arrow statement, right? That's all that we mean by the arrow statement, is that if this is true, then that's true. So we're just literally saying, well, if that's true, I'm going to be able to show you that this guy is true. So this is just CP 3 through 8, right? It's always through when we do subproofs because it's a chain of reasoning. Okay, let's look at a slightly more complicated example of this. Or, you know what, let's just look at another example before we even complicate it. So what if Q or R, and then, yeah, sure, if last time my conditional already had a not R there, so let me put a not. Okay. Yeah, we'll just leave it like that. Right, so you can try to just jump in with our old school logic rules. The first thing we can do is a simp to line 2, but already, again, I don't think we should, that's fine if you want to do that, and a lot of people suggest always starting by scanning your premises and seeing if there's really obvious rule matches, and that is a great way to start. Sometimes there's just obvious things to do. But my recommendation as the first thing to do each and every time is always look straight to the conclusion first. And ask yourself, is the main operator a conditional? Here, it is, right? And obviously, it's going to be because I'm showing you examples of conditional proofs. So I'm setting it up like that, right? So just to be clear, if it was something like this, then I can't do a conditional proof. Even if it was something like this, I cannot do a conditional proof for that, right? Because here the conditional is inside, it's not the main operator. So neither one of these would I have done a conditional proof for. It's when I see that the main operator is an arrow, then I say, okay, I'm doing a conditional proof. And right, that's always the first thing I check whenever I do a proof. I always ask, is my conclusion a conditional? Because as soon as my conclusion is a conditional, I'm doing my method. I'm just going to say, all right, everything to the left of that conditional, I'm going to wrap in green. Everything to the right of that conditional, I'm going to wrap in red. And now what I'm going to do is I know conditional proofs always have the same exact form. And I'm not even going to forget all the details. I'm just going to look at my notes and see, okay, what's the form for conditional proof? It looks like this. Right? I'm not doing any sort of creative thinking or anything right now. This is just, you should be able to do this as soon as you see that that conclusion is conditional, you should be able to do exactly what I'm doing. Or obviously, you don't need to do it with colors and whatnot, but you should be able to think through this process. Right? So as soon as you see that that conditional is that conclusion is a conditional, wrap the left side in green and wrap the right side in red, and then fill in the structure that CP always has. CP always has the same exact structure. So what's green? Here, it just happens to be just R alone. Before, it was like not P or something, right? However complicated it is, put all that right in there. Same thing down here. We're just going to take whatever it is on that right side. I'm just going to put it in. And, I mean, they don't change, right? The green is still green, red is still red. And notice how this thing down here is always going to be exactly what your conclusion is, right? If not, then you're not setting up your CP right. So the last line, which sits outside of the subproof, should always be exactly your conclusion. The start of the subproof should always be the antecedent of the conclusion, that left side of the conditional. And the end of the subproof should always be the right side of that conditional, right? So again, all of this you should be able to set up immediately without any sort of creativity or critical thinking or anything like that. All of this we get for free. And also notice how I haven't even paid attention to what my premises are. So I can set up a CP just by glancing at the conclusion, saying, oh, boom, that's all going like that. Okay, I'm going to set all of this up regardless of what's going on with my premises. It's another reason why you don't do CPs to premises, right? We don't care about looking at the premise when we're doing a CP. It's only once we've set up the CP and we're worried about making all this work, then you can start thinking about how to use the premises. But at this point, we did everything just based off knowing the conclusion. So again, I can't stress that enough. In order to do it, you should know how to do a CP just by seeing the conclusion and setting up this structure. And you should just cover up the premises up until that point. Okay, now that we have this, now we can start actually trying to make it work. So one thing we can do is the simp on 2 that I held off on earlier. So that's just going to be a 2 simp. Right, and so we could also do, so these every line always has a new number. We don't know what these numbers are yet because we're not sure how many steps it's going to take us to get to them. We just know that's the way our proof will end at the end of the day. I don't want to not put it down there because it is so easy to forget. Like, even when I'm doing these proofs myself, I always put this at the end of the day just so I remind myself where I'm going. Right, and so the idea is now I could also do another 2 simp to give myself C, but if you think ahead, C actually, I mean, it doesn't even occur in premise 1. It doesn't occur in what I'm trying to get to, right? Right. All I care about right now is just this guy right here, and C doesn't look like it's going to help me out. If you're not comfortable with that sort of like foresight, oh wait, how do I know if C is going to help me out? Be fine. Do both simps every time you see simp. That's totally fine. For our purposes, though, we don't actually need it, so we don't have to do simp. The idea is you only have to do what you actually think is going to help. On 5, what I see is I have a near miss for DS, right? So if so now that I have my CP set up, we can go ahead and erase that so it doesn't confuse it. So now when we're looking through and we're thinking of DS, we can go through and we can say, right, so DS says you have this, you have that. that. Right, so DS says you have some disjunction, a left or a right. Then you have the negation of that, or one of those sides, right? It doesn't have to be the right side. So I'll switch these out, right? We could have just as easily done, right? It just, if you negate one side, you get the other side. That's all that's going on with DS. And so the idea here is we can go ahead and link that guy up there. So this, right? And then we can link. So what we would like to do is match this guy to this guy. But it's not exactly right, right? So what's in our red box? What should we be able to, if we've already found this up here, that means the green we're supposed to be able to find is P and Q, and the R that we're supposed to, or anything in the red box, is that not R, right? So that means we need to find this over here, not R, and all we have is R. But if you remember, that's actually close. We have that rule, double negation, that allows us just to throw on two tildes as we please. Because the idea is they in fact are the same sentence. To say it's not the case that R is false is just to say that R is true, right? So this is just going to be 3DN. And so now, right, now I've set myself up and actually I do have a match, right? That now I do have not R. And so now I can give myself the green part, P and Q down there. So you know what, I'll even just throw that right there. You can just do this. So it's important that like, so one thing people might get stuck on is like, just if you, like for instance, if you're drawing it out like I am right now, and then you just leave those colors sitting there, it's important that you're flexible with, okay, right now this is like the green part, but who knows, maybe it's the left-hand side of this conditional, but maybe it's also the right-hand side of this disjunct. So it's important to be able to just be flexible with how you work with these rules. Okay, so 6 is just going to be a DS with 1 and 5, right? And I haven't, so I should just, right, we're trying to get to Q and D. And then if we can do that, then we'll get our conclusion. Right, so that's how the proof is supposed to end at the end of the day. So let me go ahead and take that out because we're running out of room right there. Right, so now we need to figure out how do we get from P and Q, and right, we get to use everything else we still have, and how do we get to Q and D? And well, we already have D, so really all we need to get is Q, and then we can just conjoin them. So here we can just simp off the Q from 6. And then on 8, we can conjoin them. So 8, so we can just put it right over here. 8 is in fact going to be that last line. Finally, we found out what line that's actually going to be. And the way we got to that last line was we just took 4 and 7 and conjoined them. And now we know this is going to turn out to be line 9, and the CP is going to run through 3 through 8. Right. So again, the idea is we're saying, if you assumed that R was true, I can show you that Q and D has to be true. And that's all that it means to believe that if R is true, then Q and D is true, right? We're not, neither one of us is convinced that R is actually true or that Q and D is actually true, or at least not as far as this argument goes. We're just convinced that if you start off believing R is true, you're going to have to wind up believing Q and D are also true. Okay, so let's look at a slight more complication before we look at the next subproof. So let's say we had, a conclusion that looks like this. Right, and so then so let's say I'm just going to give it one premise. Now, this problem actually wouldn't be terribly hard for us to do with our old school rules, with just the simple step-by-step rules. This is actually like a perfect match for MI, and you can actually do an exportation right after that, and you've already done it. But what I want to show you instead, and so actually in that case, you might have even saved a slight bit of time by not doing a CP. So it is true that sometimes maybe you can save a step or two by not doing the CP, by just noticing a couple cool tricks to do. But I mean, even in cases like this, I still recommend always asking first, can I do a CP? The occasions where it's going to be more easy to do it, like to do it without a CP, are so rare that I don't even think it's worth the mental energy in checking on that first. I think it's so much more useful if you just walk into a proof and you just say, okay, is my conclusion a conditional? If it is, I'm doing a CP. And then from there, sure, it might be an extra line, but even the times where it makes it an extra line, it's not like it's actually even making it a lot harder. It's just making it just slightly longer. So 99% of the time, it makes it much easier. 1% of the time, it just makes it a tiny bit harder, or not even harder, but a tiny bit longer. So I still always recommend just check first, is my conclusion a conditional? So that's what we're going to go ahead and do here. And so when we check if our conclusion is a conditional, what we need to do is, right, the question isn't just, does my conclusion have some arrow in it? It's, is my main operator a conditional? Right? So what's the main operator here? So the main operator, it's not this guy, right? Because this guy is only looking at R and Q, right? It's just saying if R is true, then Q is true, right? It has, like, in a sense, it has just no idea on what's going on outside of it. This is the operator that's connecting the entirety of the sentence together. That's the main nail that's holding everything together. So the idea is, once you see that the conclusion is a conditional, that main operator is a conditional, then we're going to do our process. We're going to say, okay, that means I've got a left side, and that means I've got a right side, right? Just whatever it is on that right side. That's my right side. And so the idea is, we're just going to take, right, let's do this, boom, boom, boom. We're just going to do, oh, why can't you just let me do it? Okay, this works so much easier in my head. I'll just stick to the curved lines, I guess. Right. So the idea is, as soon as I see that my conditional, or that my conclusion's main operator is a conditional, I'm just immediately just going to put out the CP structure. So, right, I can't emphasize this enough, which is why I've been repeating it, that as soon as you see that the main operator of the connective, or the main operator of the conclusion is a conditional, I haven't even looked at my premise. As soon as I see that, I draw that out. I'm not even really looking at what's on either side of the conditional. I just see that the main operator of the conclusion is a conditional, and I'm drawing this out. And now all I have to do, I mean, none of this is creative. None of this is hard or critical or anything like that. It's just noticing what the main operator is, and then putting this picture down. And now I just fill in, okay, what's green? P. What's red? R implies Q. What's green is P, what's red is R implies Q. Boom, done. And now I ask, all right, cool, done with that. I can throw away my colors. I've got all that set up. Because now, right, I don't even care about that conclusion anymore. Because this line, it's going to come for free as soon as I make this thing work, right? That's the whole point of the CP, is all I need to do in order to make this conclusion hold, all I really need to do is show that P really leads to Q. And then I get this thing for free. So I'm not thinking about my real conclusion at all anymore. That's going to just be free at the end of the day once I get my subproof to work, right? So now, throw those colors away and let's just get started. How do we get from P, as well as our premise, to this guy? And now, actually, again, we want to do the same thing that we do whenever we start a real proof or a full proof. We're going to want to do when we start a subproof. And I haven't made this point yet, but we're actually going to want to do this every time. So far, what we've been trying to get to has been something that looks like Q and D. And so when you look at it and you're like, okay, I want to get down there, well, it doesn't matter, like it's not a conditional, so it didn't matter. But think about if it is a conditional, like this case, right? If I want to get to a conditional, right? I mean, a subproof is, in a sense, like just treat this as its own proof. Just treat this as the proof. Premise 1 is not P and R imply or Q. And now premise 2, just think of that as P, and then just think of your conclusion now as just R implies Q, right? And then immediately you should be doing the same thing we did already, or the same thing you do in any proof that you see the conclusion is conditional. You're just going to set it up that R is going to lead to Q, right? This is going to be green. That's going to be red. And then, so green, red, and then green implies red. Right? So the point is, as soon as you have that subproof set up, cool, forget about the last line, forget about everything outside of it. Now just think, how do I make this subproof work? And when you're just trying to think, how do I make a proof work? Well, let's just ask the same question we did before. Is my conclusion a conditional? Because now we're going to do the same thing. And so this is what's known as a nested subproof. We haven't dropped out this assumption yet. We're going to give ourselves a new assumption, though. So let me declutter that just a tad. Now we're going to assume R, right? So what I'm doing here is I'm saying, oh, so now you have a new conclusion that you're trying to get me to. You're trying to get me to believe that R really implies Q. So that means all I need to do is set up a subproof. Again, I'm just going to refer to my notes on CP, and I see, oh, I just need to draw this picture. That's all that I need to do for a CP. If I ever am trying to get to a conjunction at the end, or a conditional at the end of the day, I just do this picture. So this is going to be CP, and this is going to be assumed, right? So all I've done is made the same exact picture just inside that one. And if this inside the red happened to be another conclusion, it happened to be A and B down here, not Q. A leads to B. Then all I would have done is just start another one, right? So the point is, once you have that subproof set up, then you just ask, all right, now let me start from scratch. Okay, so now how do I actually get to the end of that subproof? Okay. And so now we have that subproof set up, so we can, in fact, let's just go ahead and do what I said. So now let's just again, well, so we need to get from R now to Q, and let's just ask again, is my conclusion a conditional? Because if it is conditional, I'm just going to set up another subproof inside, put the left side up here, put the right side down here, and then I'm just going to make that work. However, this one's not a conditional, right? Eventually, you won't have just an infinite amount of conditionals that you're breaking apart. Here, we're just trying to get to Q. So what we can do is, so this is line 2, that's line 3. Well, what we can do is we can set up, well, either a DS or a modus ponens, however you'd like. So let's go ahead and do the MI to 1, right? So that's just going to be P and R implies Q. And so that's an MI on 1. So there's a number of different ways we could have done this. Right, but let's just stick with this. The inner part of this proof isn't the most important thing right now. The most important thing is just being comfortable with when to know to set up a CP. And if you know how to set up a CP, that's all there is to doing a CP. All this stuff in the middle is just old school logic. Right? Okay, and so then we can conjoin the P and the R because we're still assuming P, we're still assuming R. And so that's just going to be 2, 3 conj. And then on 6 is where we actually get Q, because now we can use 4 and 5 and do a modus ponens, and that gives us 6. And so now what we've shown is if we assume R, I can lead you to Q. So R really does lead you to Q, and I've shown you that given the story that runs through 3 through 6. And now this story, now that also completes the story that if you assume P, then you'll believe that R really leads you to Q, right? And it doesn't matter that I had to tell you another story to make you believe this story. The point is, I was able to start a subproof off with P and then end it with Q, or excuse me, not Q, but this sentence, if R then Q. And that's all that it means. That's all that it takes in order to show you that P really does lead you to that right side, is that we started off a subproof with the left, showed you that it runs to the right, and that's what it means to show you that the left leads you to the right. It doesn't matter what type of sentence is inside here, right? And so that's how we get our conclusion, and so this one is just going to be 2 through 7. Okay, so that's conditional proofs, and that's also nested subproofs as well. Right, so don't get overwhelmed by nested subproofs. It's not really going to be, as long as you know, once you're inside a subproof, you are just treating that as kind of its own subproof, then nested subproofs won't be such an issue. Okay. Now let's look at, actually one other complication before we look at reduction to absurdity. Okay, so if that's my conclusion, we're trying to convince somebody that P and if Q then R. P is true and Q leads to R. Right? And let's say that I believe P and L, and I believe right, not Q or R, right? This is going to be another proof that we could do with our old school logic, but I'm going to use it nonetheless to make this point. Okay, so let's go ahead and do this. You know what? I'm going to actually shift this up a little bit. You know what? Never mind. It's not worth it. Okay. So the idea here is we first are still going to be good logicians and check is my conclusion's main operator a conditional. So we do have a conditional in the conclusion, but the main operator is actually a conjunction. So I can't do a CP. But what I could do, so then I jump back over to my premises and I realize like, okay, I've got to start off with some sort of just old school logic rule. And look at this. Luckily, premise 1 is just going to be set up nicely for a sim. Right. So actually, yeah, no, I think I do want to change this just slightly to make the point. So bear with me for just a second. Okay, let's go ahead and look at this example instead. So I've just changed it up just slightly. So our conclusion is just still P is true and Q implies R, but now premise one is P and L are both true. Q implies J, and L and J imply R. And so we want to get to this conclusion. Right, so our main operator is not a conditional, it's a conjunction. But you might be able to tell, well, really what I want to get to is just two different things. I want to get to P and I want to get to Q implies R. And then at the end of the day, I can just conjoin those things. Right, and then there's my conclusion. And so I can just kind of think of about this as going in two parts. So whenever your conclusion is a conjunction, you can, I mean, sometimes this will be more useful than other times. This isn't as universal of a good idea as the CP. But a lot of times, if your conclusion is a conjunction, you can think about it as in two parts. Let me first get the first part, next I'll get the second part, and then I'll just conjoin them together. And in this case, we can see that that'll actually work out really well, right? We can get P just from that, and then we can get Q just by doing, well, so not Q, we need this entailment. We can do that with a CP. So, one way we might want to do this is, well, so I'm not going to start off with my CP because, I mean, you could, but we're going to look at how making that decision is going to affect how this goes. So you might start off with something just like a simp, because one is just asking for it. So simp to one. And then we would do it twice to get both sides. So simp one. Right. And so the idea here is, okay, cool, we've got P. So now we need to figure out, how do I get if Q then R? But again, if at one point you find yourself saying, hey, I need to get to a conditional, that just means do a CP, right? If you need to get there, all we're going to do is just do a CP where the start of it, we're going to assume Q, and then we're going to try to get at the end of the day to R. And if we can do that, then we've really shown that Q leads to R. 6 through something. Right? And so the idea here is that we can still do a CP, and it's not going to get us to the entire conclusion, but we're doing the CP because we see that there is still something we want, that once we get that, it's going to help us get to a conclusion. So if you can see that building some conditional will in fact get you the conclusion, like, I mean, a lot of times maybe your conditional is just a conjunct of the conclusion. You can do it still a CP inside of your proof, and then end that CP, and then continue on your proof. So let's see this a little bit more cleanly. Let me write this up a little bit more nicely. Okay. So in this case, we can say, all right, so 4 is P 1 simp, 5 is L 1 simp, 6 is, now we're going to start the subproof. 6 is assume Q. And then 7, so now we have that modus ponens match. We can get J from 2, 6 modus ponens, right? And then, and now notice we have J and we have L, and on line 3, we see that if we can put them together, then we'd have a perfect modus ponens match. So on line 8, we'll put L and J together. And that's just going to be 5, 7 conj. Right, so all I'm doing is just citing the things that actually entail this line, right? Anytime you give a new line, you should be able to exactly say why you know that that thing is true. It has nothing to do with the fact that you're planning ahead to use it on 3. That's just going to be the next line you talk about, right? So let me give myself more room right here. So on 9, finally we can get ourselves to R, and that is going to be the last, because we were just trying to show that Q really leads to R. So line 9 is going to be justified just by 3 and 8 modus ponens. And Q implies R. We know this is true now on line 10 because, well, I told you a story that started on line 6. It went through line 9, and it was CP. Right? And so now on line 11, so we're not actually done with the proof yet, because on line 11, now we actually put P and if Q, then R together. And that's just going to be a 4, 10 conj. And now finally, we're done with the proof. So in case it hasn't been clear yet, we never end a proof inside the subproof, right? Because that's basic. That's as if you're making an extra assumption, right? The guy you're talking to is only okay with making this assumption if we discharge it, as it's called, at the end of the day. So after I end this subproof, I'm no longer assuming that Q is true. I'm not at all. I'm only assuming, now I'm back to only assuming that my premises are true. And now the idea is, based on the story, I'm showing you that if you assume Q is true, then you'd get R to be true. I'm not telling you you have to believe Q is true. The point in this subproof is I'm just saying, if you accept that Q is true, then you'd have to accept that R was true, right? So just to make this to show a little bit more of a variation on this, let me go ahead and move. Didn't mean to resize it, but I guess that helps too. So this was 10, and it was Q implies R, CP. So another way that this proof could have gone is if we still had 1 is P and L, 2 is Q implies J, and 3 is L and J implies R. We still have the same old conclusion, right? So same argument. And right, so oops, let me. Right, so same argument, but let's just say that we did start our subproof off first, Q, and we're trying to get to R at the end of the day. So assume. Then the idea is, okay, well, you can still do the simp inside here. So that's 1 simp. And then we can do L1 simp. So this would be 4, 5, 6. Right, and so we're going to need some more room here. So you can do the simp inside there, and we would end up doing the same game that we did before, where we get J, and then we're going to put L and J together, and then we do modus ponens to get to R. So this is all going to work more or less the same way. But the idea now is, once we're outside of that subproof, well, let's think about it. You've gotten from Q to R. So remember, the subproof is the subproof has one sole purpose in life. It has one moral of the story that it's trying to make, and that's just whatever sentence we put after it. So the point of the CP is always just to show that Q implied R. All this extra work you did in here has absolutely no value other than to show Q implies R. CP. So at the end of the, so let's just say that it took you to line 9 to get there, or well, so I guess we know how many. It would be 8, 9, and then 10 right there. What you cannot do at this point what a lot of people would want to do is just say, oh, let me just get my conclusion now. I've got P on line 5 and I've got Q implies R right there. Let me just conjoin them then. Right? That sounds really intuitive. Boom, done. But that's wrong. And the point is, because as soon as you leave that subproof, this is very vital to understanding subproofs. As soon as you leave this subproof, you no longer can grab anything from inside of it. Because all of the stuff that happened inside the subproof completely depends on this extra assumption that you're making. And so the subproof is only good for showing like what happens when you make that assumption. So when you make the assumption Q, R is going to be true. So that's all that the subproof can show you. It doesn't actually show you anything in here is true. So we can't do a conj right away. So what we have to do actually, that thing that we did on line 1, instead of, we could have either done it ahead of the subproof, or we're going to have to just do it again outside of the subproof. We're going to have to do a simplified 1 to give ourselves P. And then now on line 12, now you would be able to do the conj. Because now you have two things completely sitting outside of subproofs, and that you can look at. But you can't grab anything from inside a subproof unless you are already inside that subproof. If you're inside a subproof, you can look outside of yourself. That's totally fine. Or if you're inside like a nested subproof, you can look at like the parent subproof or whatever's outside of it. But you can never look into the subproof to get anything particular. So it only goes one way. If you're inside the subproof, you can use everything outside of you, unless it's in a different subproof that you're not a part of, right? But in that case, right, so when you're not in a subproof though, when there's a subproof you're not in, you've ended that, then you can't use anything inside. Okay. So that's conditional proof. Let's go ahead and just, let's look at RAA, which is the other subproof. So all of what we've done here has had the same form, and really maybe we showed this early, but it would be even good just that we can see it. It always has, a conditional proof always has the same exact form, right? So this is what should just be memorized, or, you know, and when I say memorized, I don't mean like textbook style, like you're just memorizing dates. This needs to be just natural, that when you think CP, you think that structure every single time. And more to the point, this is what you do this when you want to get to that line right there. When you want to get to some conditional, then you do a CP, right? And so that happens when your conclusion is some conditional. But again, just to again, I don't know why people do this. That's not about when your premise is a conditional. That's totally different, right? You're not doing a CP to prove, because we already believe our premises. I'm not going to belabor that point again. But yeah, I typically, if I ever see someone doing a CP to a premise, or even saying the phrase prove a premise, I immediately, right, that tells me basically that you have no idea what's going on. Okay, and if you want to know why, I mean, just rewind this video and rewatch. Did we ever do a CP to a premise? No. Okay. So this is what a CP looks like. Now, and we do that if you're trying to prove a conditional. The other subproof technique that we have, so this is conditional proof. In fact, let me just be better about space. So that is, no, I don't know. Okay, the other proof is called RAA, reductio ad absurdum, right? Or proof by contradiction. So reductio ad absurdum is just Latin for reduced to absurdity. And so the idea behind this is we're just going to reduce some assumption to absurdity to show that it's false. So if I wanted to prove somehow, if I wanted to prove to you to believe that A is false, to believe not A, right? So I'm going to have maybe some premises up here. But the idea is, well, maybe I don't know how to just easily just, use our old school rules just one by one to end with not A at the end of the day. Well, one thing I can do is I'm going to, again, use a subproof. So again, right, a subproof is always going to be this box, always going to be a bar like this. And the idea is we always start with some assumption. And this assumption is just going to be a single thing where it's just, okay, well, what if this did happen? And then we're going to show what the result of that assumption is. And then we're going to get a moral of the story at the end of the day. Right? So we're telling a story, and then we're going to derive a moral at the end of the day. And that's the same thing up here, right? We told some story, and then the moral of that story is just that P really does lead to Q, right? The story is, if you start off living like this, you'll end up dying like this. So that means living like this really does lead to dying like this, right? That's all that's going on. That's what's going on with CP. And in general, that's what's going on with these subproofs. So the specific form of the story for CP is, if you start like this, then you end like this. So the moral that you get is always, if this, then that. But now the form of RAA is slightly different. So the form of RAA, again, we're telling some story to derive a moral, but now the idea is we're saying, assume, oops. So so the idea is I'm going to take, so this can go in two different ways. Let me show you the other way. So instead of, I'll replace it with what I just had in a moment, but this might be an easier way to start. So the idea is, if I want to, let's just start with A itself, not the not A right now. We'll just talk about, I want to prove that A is true. Let's say I want to prove that just some proposition is true. Any proposition. I want to prove that it's true, but I don't know how to get there step by step. Well, one thing I could do is I could suppose that it's not true. Okay, so I want to prove that it is true, so I'm supposing the opposite. So it's like, okay, you don't agree with me, so I'm going to entertain what you have to say for a minute. You don't believe that the sky is blue, so I'm just going to say, well, what if the sky isn't blue? So again, this is an assumption. I'm not guaranteed to believe this. I'm not actually saying as a fact that the sky isn't blue, that A is false. I'm just saying, all right, I'm going to tell you a story then. And this story is going to start off with, suppose that I was wrong. Suppose that A isn't right. Right? Suppose I was the opposite of my conclusion is the case. Okay? And what I want to do from that is I want to show you that that is absurd. And so the idea is, I'm telling you a story where, right? So I'm telling you a story where if you start off believing this thing, it'll lead you to craziness. It'll lead you to believing some absurdity, something nobody wants to believe. So that means you shouldn't believe that thing, right? If believing this means you're crazy, then you should turn around and not believe that thing. So the way that this is going to work is we're just going to put the moral of this story is just going to be A. Right? So if you start off assuming that A is false, and that leads you to being crazy, then that must have meant A was true all along. Because whenever you start off with it being false, that means we're crazy. So it must have meant that A was actually true. And we actually can do the same thing in the other way, right? So if I wanted to prove to you that A was actually false, then I could do the same thing in the opposite direction. I could assume that it was true, get you down to some absurdity, and then you'd have to conclude, okay, then it must have been false at the end of the day. So the idea with RAA, it's kind of just like a negation introduction or something like that. Or we're just saying, I'm going to tell you a story where you suppose anything you want, and then if I can reduce that to some absurdity, then you better turn around and say, then that must not have been true all along, right? So that's what we're going to do with RAA. Let me go ahead and give you the same form that we have for the color coding that we have for the other one to the right. So the idea here is if you have something, right, so there's just going to be one now. So here, so right, okay, let me change this. So this is basically how RAA is going to look, and it's just a matter of these two things differing in a tilde, right? So we could just as easily define it like this, right? If you assume that this thing is true, you get out of it at the end of the day that it's not true. Or you could just assume that it's not true, right? And then, so if you assume that it's not true, then at the end of the day, it must have turned, and you can reduce it to absurdity, then it must have been not true. Or it must have been true, right? If we assumed it was not true and we can reduce it to absurdity, then it must have been true. So, okay, I mean, hopefully that makes some sense, right? If I can start off with a belief and then show that it's absolutely crazy, then you should turn around and after the story, you should be like, okay, the moral of that story was I'm not going to believe that anymore. So that should be all right. The question is, what is this absurdity? Okay, so in logic, absurdity just means contradiction. So let's think about just quickly the truth table of something like this, right? Okay, so let's do the truth table for that sentence right there. Oh, wait, what am I doing? I'm putting it on the wrong side. Okay. So how many atomic sentences do we have? Well, we just have P actually. So this sentence is just saying P is true and it's not true. So this is what we call a contradiction. And I'm going to show you why we hate contradictions. Well, I mean, in some ways they're useful, but they're only useful because of how much we hate them. We hate them because they're never right. That's the point of a contradiction, is that it's impossible that it's ever right to believe a contradiction. So we're going to look at every possible way the world could go. You know, P could have been true, but P could have been false. Right? Those are the only two ways the world could go. So let's go ahead and do it. So if P is true, so I'll go ahead and just copy a true down under that. Not P, though, is going to be false. And so the and is going to be false because it's flanked by two, or it doesn't have a true on both sides. And then down here, so if P is false, then P is false, and then not P is going to be true. So then the and, again, is just false because it's flanked by a false and a true. And it needs two trues if it's ever going to be true, right? The and is saying two things are true. So the point here is it's never going to be true that P is true while P is being false, right? So this would be very intuitively crazy that you would ever believe snow is white, but you would also say snow is not white, right? Or you would say God exists, but she doesn't exist, right? You never want to believe a contradiction, or at least you're going to be illogical if you do, right? So the whole point of this class is figuring out which beliefs can actually can be true at the same time. And these two beliefs, that P is true and that it's not true, those cannot happen at the same time. You cannot simultaneously believe that P is true and then believe that P is not true and be right about that, right? So the idea is this absurdity, instead of looking at absurdity, what we want is a contradiction. And a contradiction is just anything of this form, anything of the form stuff, I believe something's true, and I don't believe it's true, and I reject that, right? So global warming exists, but I don't actually think that it exists, right? No, you have to make up your mind. You have to either choose global warming does exist or choose it doesn't exist, or clarify better what you mean by the proposition, right? So that's another thing about logic. Sometimes it'll show you you're just being ambiguous on what you talk about. Maybe you need to be more careful about what you actually think is being true. But right, that's all the material for a true to form philosophy class. So instead of absurdity right here, we just want anything of the form stuff and not stuff. So really, this doesn't even have to be whatever, this doesn't even have to be related to what you started with. This just has to be something, anything that has this form of stuff and not that very same stuff. Okay. So again, the idea behind an RAA is you're trying to prove this guy. You're trying to prove something like A at the end of the day. So we assume, so if you're trying to prove A, you assume not A. And then based on assuming not A, we're going to be able to get down to believing P and not P. So if I can show you that assuming not A will lead you to this contradiction, then you should turn right around and not believe, and believe the opposite of what we started with all along. So sometimes it will happen. I know some of you are thinking, where do we get the blue ones from? So sometimes maybe it is that you can get to just A and not A. But the point is, you just need to find any contradiction. So you might have other premises above, for instance, and that's where you're going to be able to derive the contradiction. But the point is, you just need something of the form stuff and not stuff. If it's A and not A, cool, more power to you. But it might be P and not P, or it might be Q and not Q. Or it could be something like this, L and J and not L and J. Bless you. Right? Or it could be something just weird, right? It could be P arrow Q and not P arrow Q, right? That's why I'm showing you these things in with the lens of these colored blocks to show you it's just, do you have the thing and then that same thing fitting into this form? So the things you need to pay attention to here are always going to be just the colors tell you, right? So now we use this. So now these colors are telling you just generally, you need just some sentence to fit in right here, and you just need that same exact sentence to fit down later. And they can always be as complicated as ever. Like they can be ridiculously complicated in any case. But the point is you just need to have that full sentence in any of these blocks. And so in this case, right, you just need to make sure you can fit this form. This is the form you need to have in mind when you're thinking of RAA. This is the form you need to have in mind when you're thinking of CP. And then we can do it. Okay, so I'm going to try to keep this. So before I do that, I'm going to clean this up a little bit. Oops, not that much. Okay, so one thing, do this. Why did you not grab everything? And then those to the same size. Really? Okay. So these are our two subproof methods. So if you're ever going to start a subproof off, if you ever find yourself drawing a line, you better know exactly how it's going to be structured. Just generally, like you should know exactly how that is supposed to end. You might not know, like for the case of the RAA, you might not know specifically what's going to be the contradiction, but you better know that there's a contradiction down there, that it has that form. And you better know exactly what the end of the, like after you finish that subproof off, you should know exactly what that looks like. So just like knowing the rules, like when I say you don't know a logical inference rule unless you know how many lines it's citing, right? Because that's what, because that determines like that you understand, that you know the structure of it. Similarly, you don't actually understand these subproofs. So this one's RAA. You don't actually understand these subproofs until you're thinking about them in this sort of lens, until you're thinking about them as just, okay, I always know exactly, or at least, so in the case of the CP, you know exactly how it begins and ends. You know exactly how it begins and ends. In the case of the RAA, you know how it begins exactly, and you know how it's supposed to end generally, and after the subproof, you know exactly what that's supposed to be. So the only question on what's even going to fill in these boxes here is just these two blue boxes. They have to be exactly the same, but that's the only question in any of this if you're setting up a subproof of what should be there. So let's go ahead and do an example of an RAA real quick. So the idea is if we had something like if P then Q to not Q and R or something like that. And we want to just prove that not P is true. So again, this is another, like most of the examples I've given today, this is another case where we can actually really easily solve this with some straightforward logical rules. But I just want to give you the idea of like how an RAA works. And so the idea is, if you didn't know how to do this, if you did hit a wall, so RAA we're typically only going to do when we don't know what else to do, actually. So if you're not sure where to go, then one thing you can do is just say, okay, well, suppose my conclusion's false, and see what happens. And so here, we're going to just assume that my conclusion's wrong. So I'm just going to assume that P is right. So if I want to prove to you that P is false, so I'm going to assume P is right, is true. And then the idea is, right, so I just need to match this structure. So here, right, so I mentioned earlier, you could either have the negation up top there, or you can have the negation down below. The point is, it's just that the first thing and the last thing are going to differ by a negation, right? So it's that you either start off with believing it's true and you showed that it's false, or you start off by believing it's false and you show that it's true. In this case, we're going to assume that it's true, and at the end of the day, we're going to get not P, right? So this is just boom, boom, and now we have a perfect match right there. And so now the idea is we just want to get something of the form P, or blue and not blue, right? I'm going to use letters. Okay, so we just need something of this form. All right, so let's go ahead and try and figure out how we can get there. So for, we can do a real obvious modus ponens there, and that'll give us Q, right? So from 1, 3 modus ponens, we get Q. And then notice on 2, we can simp that, and we're going to be able to get not Q. So that's just 2 simp. And then right from there on 6, now we actually have it. We have Q and not Q. So blue and not blue. Right? So all I needed to do was just find something that I would be able to put in this form. I didn't know that it was Q ahead of time. Maybe it was going to be P, right? There's going to be actually a number of different ways that you can do this proof. You can find a bunch of different contradictions, but as long as you find one contradiction, then we're okay. So right, this was just me finding those things. And so right here, this is just me pointing out, oh, in 4 and 5, I conjoined those things together. So typically the last line inside of an RAA is a conjoin. It's you pointing out that contradiction. And then after I finished my story, after I showed you that assuming P really does lead you to absurdity, I know then that because of the story on 3 through 6, then not P actually has to be the case. So this is how an RAA works. Generally speaking, you're going to want to do this when you hit a wall. RAA will always work. It gives you an extra assumption, and all you need to do is just find some contradiction, just any contradiction. So this will a lot of times be very helpful as you're going. Right. So that is now RAA. So all we do is we assume something, we try to find any contradiction, and then we get to put the opposite of that thing. So the point is, if you ever want to get to a statement, whether that's a negative statement or a positive statement, just put the opposite of that up here. So if it's a negative, put the positive version. If it's a positive statement already, just put a tilde on it. And then find some contradiction. And once you do that, you can just stop your subproof and say, okay, I get the opposite afterwards. Okay. So let me go ahead and, okay, so let's go ahead and just look at this, this example argument now. Just to get a little bit more experience with these proofs. So the first thing I'm going to notice is that my conditional, or my conclusion, is in fact a conditional. That conditional is the main operator. So I'm immediately going to look over and I'm going to just want to draw exactly the picture I have over there. So I know I'm going to have to start with my left side right here. And at the bottom, I'm going to have that same picture. So right, all I'm doing is just copying and pasting, mentally copying and pasting. Again, if you're not doing that whole thing right away, it's because you think that you're able to skip steps, and it's because you're trusting yourself to be good enough, disciplined enough, smart enough, whatever, to remember how to do it at the end of the day. But 99% of the time, that's also paired with the people that are also actually struggling and that are having a lot of difficulty in grasping these things and really figuring out how to use these. So the only way, I do this every time. I draw this structure out every single time. The only way I would say you don't do this is if you happen to be, I mean, yeah, again, I do it every single time. If you don't want to do it every time, fine, but I would only say stop doing it every time if you feel absolutely comfortable. So some of you are going to feel just fine as soon as you see that to set it up. But the idea is when you set this up like this, we know exactly how it's going to end. And it's just so easy to forget how it's going to end unless you set it up like that. Also, setting it up like this, I mean, it just forces you to make sure you know what's going on. If you don't feel comfortable setting it up like this, then that should be a big red flag that you need to spend more time setting these things up. Because if you don't feel comfortable just setting up that picture, then you should not even be trying to touch doing the CP. Setting this up is doing the CP. That's all that it means to do a CP, is just to set this up. Everything in the middle, that's old school logic. To do a CP is literally just to know how to set that up, right? And then everything that happens in the middle is just old school logic. So again, I mean, I know I've been beating this horse throughout, but put the entire structure down as soon as you see that. Don't try to skip steps. The whole point of what we're teaching you guys is to not skip steps throughout all this. Okay, so what's my left side? It's P. What's my right side? It's Q and R. Okay, so now all we need to do, really easy proof. How do we get from P to Q and R? Well, all right, so let me go ahead and go ahead and take this stuff. Actually, I'm really enjoying that we can do that. It's actually really cool. Okay, just want a little bit more room in there. All right, so the idea is we just need to get from P to Q, then or Q and R. All right, so first thing you can notice is, oh, look at that. I have a great modus ponens waiting for me on 1 and 4. That'll give me S, so 1, 4 modus ponens, right? And then, you might start to think, okay, well, what else can I do from here? There certainly are ways to make this work. I want to try to find, right? So you might, so another thing you might notice, or that you should actually get very comfortable noticing, is that 2 and 5, right? That is a near miss for DS. That's going to be a very, very common near miss for DS. So right, DS is saying if you have P or Q, then you have negative P, you can get Q back. But the idea is the second line always has to have an extra tilde. Here, they disagree on a tilde, which is what we want, but we wanted the second line to have an extra tilde. So right, we've handled this already in some examples, but just making it more clear. So you'll see this a lot. A near miss for DS is going to be when you have that or, and you have the opposite of one of the sides, but it has one less tilde instead of one more. And the way we're going to take care of that is really simple. Why did I write 8? It's really simple. We're just going to throw 2 tildes on S, right? Because that's just DN. We get to do that. I mean, this is why being comfortable with these rules is so important. You know, you can see I have one less tilde that I want, but I actually want to have one more tilde. Right, I have one less tilde than the guy, but I want to have one more tilde than the guy. Well, that means I just need to increase myself by 2, and that's exactly what DN does. So, right, and be careful, we're just doing this to line 5, right? We should be able to ask the question, why is line 6 true? Why do you believe that it's not the case that S? The only reason you believe that, you should be able to tell yourself this story, and if you don't, then you need to go back and review just the rules. The only reason you believe that not S is true is because S is true. Like, think about it. The only reason just think about what DN says. The only reason you can do DN is because it's just eliminating or adding on 2 negations. Okay, I'm gonna stop beating that horse. All right. So now we have not S, and now we're finally able to actually fit that DS rule. So we get just R. And now, so we have R, we need Q and R. So we need to somehow get from Q to R, or from whatever we have here, including R, including our premises, we need to somehow get to Q and R. Because we already have R, really the idea is if we could just get to Q, then we could just conjoin them right after. So really the way we want to be thinking about this is, let me go ahead and extend this yet again. Move these guys up higher. Hopefully that doesn't look too bad. Right, okay, so it's starting to get a little ugly, but so this is just going to be a ds with, what was that? My thing is in the way. A ds with 2 and 6. Right. Okay, and so now we know R is true, but we don't know. Yeah, I think I've just got to go ahead and scoot this down the old natural way. Oh, it's so hard to draw a straight long line. Okay, I'm not going to waste time on this though. So Q and R is what we're trying to get to, right, at the end of this. We already have R, so the idea is you can kind of think about it as moving the goalpost closer to yourself. If you can just get to Q, right? So if that's line number, this is line number -1, right? If you can just get to Q, then on the very next line, we're just going to do a conj. So really the idea is, how am I going to get to Q? Because immediately after, I'm just going to do a 7 and then a number -1 conj, right? I'm just going to take whatever this line turns out to be, whatever I actually find Q on, and then the 7 line where I actually already had R, and I'm just going to put them together. So now the question is, how do I get to Q? You might be able to see, we can actually do that pretty easily with contraposition, but if you can't, let's say you actually hit a wall right here and you don't know what to do. Well, we can just go ahead and do an RAA, right? Anytime you hit a wall, we can do this. So I'm going to clean up these lines, because now with 2 subproofs, it definitely will get more confusing. So we have this guy. Oh my goodness. Right, so these line numbers are for these, they're inside the subproof. Right, so you might think, you might hit a wall and not know how to get to Q. And so anytime you want to get to something that you don't know how to get to, like we could have even done this for the bottom conclusion. It's just that there was more stuff that we saw how to do. But we can just say, all right, then on line 8, I'm just going to assume not Q. And then now I have a perfect match on line 9 for modus ponens, right? So I'm going to go ahead and beat this a little bit, right? So we have, here's my left side. Here's my right side. I have my left side. So it's going to give me my right side, right? So what am I going to put down there? It's just going to be not R, right? So again, the reason why I slowed down to do this on that one, so it's going to be helpful if I take away the color coding for the other one right now. The reason why I slowed down to do to walk you through that particular modus ponens, let's assume, right, because it's the start of our subproof, and then this is MP, is just so you're comfortable. Yeah, there's a tilde there, but the point is that whole left side, I was able to grab my whole left side down here. And all modus ponens cares about, it doesn't care about how complicated the sentences are. It just says, if you give me that side, I will give you that other side. And so that's why we were able to do modus ponens like this. Ponens, and that's 8-3. Okay, now I've got not R. And now, look at this. On line 7, we already know that R is true. But on line 9, we're trying to say that in this story, R is false. That means on line 10, we can say, point out to him, hey, you believe that R is true and R is not true. And all I'm doing is conjoining 7 and 9. And so the idea is, based on this assumption, based on line 8, based on you believing not Q, right? So we can go back to, so based on you starting off believing not Q, I was able to show you that you in fact believed some contradiction, R and not R. right? And so because of that, you should turn around and say, okay, then Q is actually true, right? So we started with not Q, and we were able to get Q itself at the end of the day, right? So this would have been the form that has, so we could make two different forms of RAA, one with the tilde at the top and no tilde at the bottom, and vice versa, the one that we have right here. Okay, so that's RAA, and so now we've gotten to Q, and so now now we can justify Q. We can, right? So we need to say, how do I know that Q is true? Well, because 8 through 10 told me this story that reduced not believing it to absurdity. So because I know Q is actually true from 8 through 10, now I can do on the next line. Now I actually have line numbers for these things. 12, 13. Right, so then this is going to turn out to be 7, 11. And then CP is going to be the story we told 4 through 12. Right, I'm sorry it got ugly there. And in general, I apologize that these aren't always the prettiest things to look at, but hopefully you're getting the idea. And as always, email me with any and all questions. Right, so more or less, I'm going to go ahead and stop there. Hopefully that gives you a good insight in terms of what's going on with the subproofs, why we're allowed to do them, and what they're able to do, as well as some sense of when to do them. Right? It should be really obvious when to do a CP. It's just, are you proving a conditional? Yes, do a CP. No, don't do a CP. So actually, CPs might just be the easiest thing in logic because there's absolutely no creativity to it. It's just, is the conclusion a conditional? Boom, do it. Is it not? Then don't do it. So that's like that might be just the one thing here that you don't actually have to critically think about. That's not even a problem-solving measure. That's just, that comes completely for free. RAA is a little bit more subtle. It's not always clear when you want to do RAA. A lot of times if you're trying to prove just some simple sentence, it can be useful to assume the negation. So sometimes when your conclusion is a simple sentence, an RAA will be more helpful. But RAA will actually always work. That's logically provable that RAA will always be able to work. It's just that sometimes it'll get more bloated. But when in doubt, go ahead and just assume the negation of what you're trying to prove and try to get to some contradiction. That's the idea there. Right, just a little bit more zooming out. So the idea here is when you're doing one of these proofs, I always start by checking, is my conclusion a conditional? Right, and I've said that a million times, of course. And if it is, cool, I set it up, and then I check, is the new conclusion, is the conclusion of my subproof a conditional? And if it is, cool, I set it up, and I just keep repeating that process until that thing I'm trying to get to is not a conclusion. Right, so in this case, right, it was only after one instance of that process that the thing I was trying to get to was not a conditional, so I didn't need to set up another CP. And then the idea is, so now that I've checked for the CP, then I go and look, okay, do I have any really obvious rule matches? So I think about modus ponens and I think about DS, and I mean, it's nice that we have these, that I have this ability to just drag and drop these things. That's the way I'm looking at it. You want to scan, do I have a premise whose main operator is a conditional? Because that's what I need in order to do a modus ponens. And then if it is, cool, I'm just going to say, all right, well, then that's my left side, and that's my right side. So then I ask, then let me scan my list. Do I have that left side already? Because if I do, I can give myself the right side. But the whole point in doing all these proofs is you need to be very comfortable in just looking at it in this sort of way, in this sort of structured way of just, okay, what's the main operator of the sentence? And that's all that matters. All the other operators, they're just going to be squeezed into these boxes here, right? So it only matters, let me just identify the main operator, and that's what tells me whether or not I can do a rule, right? So the name of the game when you're doing these proofs, whether or not you're looking for a subproof that you're trying to do, or you're just thinking of a regular inference rule, You want to see what's the main operator of that sentence. Okay, cool. What rules work on that operator, right? Because if you're not thinking about the main operators, then you're not going to be able to do any sort of implication rules. Okay. All right. I'll go ahead and just leave it there. Again, let me know if you have any questions.